Hi everyone. So, new video. This time it's on normal distribution. Um, and what is the normal distribution? Well, you might have seen it before. It's this curve here, otherwise known as the bell curve. Um, and we're going to talk a little bit about the properties of this curve, because we're going to do quite a lot of work on it, and then we can briefly explain where it's coming from. But it's a very complicated equation. So where the actual equation comes from for the curve, we wouldn't talk about, but you can see roughly how it's working. Now, what this curve is, at the moment, this is the standard normal curve, all right? So this is the standard normal, which you're going to learn later, and it used to be that you'd start off from this point. Okay, so the mean is always in the center of a normal distribution bell curve, right? The area underneath it is obviously 1, okay? So when you find the area beneath what is essentially a probability density function, so probability density function, okay? What you're going to see is actually this is very similar to a histogram, okay? Essentially this is a histogram with continuous data, okay? So it's for continuous data, and the area beneath that curve is 1. And these ends stretch out to infinity, so minus infinity, infinity, on the left and right hand sides, okay? So for a normal distribution curve, the mean is always in the center, but so is the mode, and so is the median as well. The curve is symmetrical either side. And what the normal distribution normally describes is almost any natural phenomenon. So like height, which is continuous, right? So height is continuous because someone can say, oh yeah, I'm 178 centimeters, and you go, actually you're not, because if I zoom in with a microscope, I can see that you're 178.1. Oh, but actually you're not, because if I zoom in even further, you're actually 178.00. And then, do you see what I mean? You can go on forever. So height is not discrete at all. It's a continuous value, which means that the probability of you being 178 centimeters is 0. Okay, and it will make more sense when we look at how we make this into a histogram, the origins of the normal distribution. But at the moment, we're just talking about the properties of it, okay? So the properties are, the mean is always in the center. You can see for the standard normal that along the bottom here, right, this is number 1 here, this is 1 standard deviation away from the mean. This is 2 standard deviations away from the mean, okay? And 3 standard deviations from the mean. Now, why is that interesting? Because, so what we talked about, we've got symmetrical bell curve, we've talked about that. The probability of x equaling anything is always 0 in a normal distribution. So if x is modeled as a normal distribution with mean and standard deviation squared, so variance, right? Then the probability of x equaling anything is always 0. Because the area, remember what we're doing when we're using a probability density function, we're using area. So if I want to know the probability, or in this case, of being between -1 and 0, I would find this area here, okay? But obviously the probability of being 1 is just this line here, and a line has 0 thickness. So it's 0 times the height of that line, and therefore the probability is 0. Okay, and that makes sense because it's continuous data. You are not 178 centimeters high. There is no 178 centimeters high when it comes to humans, because the probability of you being that high is 0. Okay, so we've talked about the mean, median, and mode all being in the center. That's good. And the total area beneath the curve is 1. We've talked about that because it's a probability, and probability is always between 0 and 1. The points of inflection are mu plus or minus a standard deviation, so 1 standard deviation, and you know what point of inflection means. It's when the graph goes from concave to convex and or vice versa. And you can see that that's happening here. We're going here, and then suddenly, at this point, 1 standard deviation away from the mean, because remember that's 1, your graph starts to go in the opposite kind of curvature direction, so convex to concave there. Okay. Important facts then: 68% of the data is contained within mu plus or minus standard deviation. So that means one standard deviation either side of the mean contains 68% of all your data. Okay. Two standard deviations away from the mean, right? As you can see, 95% of all the data. Okay. So 95% of all the data is two standard deviations from the mean, and 99.7 of all your data is three standard deviations away from the mean either side. Okay, so 99.7%. Why is that helpful? Well, remember the normal distribution describes natural phenomena. Okay, so if you're like a small business, let's say Boulder Brighton, they need to order a certain number of shoes, don't they? And they don't have much money. They just remortgage their homes to start that business. Okay, they need to order a whole load of shoes in because people don't want to buy shoes; they want to rent shoes. How do you know? If you know the mean, like shoe size for say men and women, then how do you know how many sizes up or down you should go either side of that before it's just not worth your while? Okay, so you notice if you go even one standard deviation either side of that mean, so one shoe size, one standard deviation either side, then you've covered 68% of all your demographic. If you go two either side, you've got 95% of all your demographics. So that's probably worth it, isn't it? You wouldn't go outside of those shoe sizes at this stage because you don't have much money. You can't buy all these shoes ready for people that are very unlikely to arrive, if you see what I mean. So it's super helpful in that respect. Okay, and just briefly on what normal distribution is then. You can see it from this kind of Excel thing that I've made here. So essentially, here's all the heights of, I think it's school kids in primary school. Okay, and I've ordered all the list, and there's loads of them down here. So, over like 4,000 of them, okay? And what I've done is I've put them into a group frequency table. So between 0 and 10 centimeters, 10 to 20, you can see, okay? And you can see they're all grouped in the middle here. So if I put that into a histogram, okay, which really is just a glorified bar chart, but so there's our histogram here, okay, and you can see there's not really much I can do here. But what happens if I make the intervals smaller, so between 0 and 5 and 5 and 10, etc.? Well, you can see what happens here. So 0 and 5, you can see my class size is 5 in width now, not 10. And you can see actually what we're starting to get is this more rounder picture, right? And then if I make the class size 1 in width, okay, so it's literally 0 to 1, 1 to 2, etc. You can see that, wow, I really am starting to get this bell curve kind of look here, okay? And that's only with 4,000 people, right? So imagine if I reduce my class size to be between, like, I don't know, it could be 0.05 of a centimeter in width, okay? And I made my n, my number of people, 1 million, okay? If I made my number of people 1 million, and my class width, I'm going to make that like 0.005 centimeters, then can you see what would happen? Your intervals between each space is getting so small, and your n has to be massive because some people are going to fit, more and more frequency is going to fit into each of those class widths. And you would start to get a really nice gradual curve like this. And that's just one example of data. You can just see how naturally these things fall into a normal distribution shape. Now, how to actually use the normal distribution then? In practical terms, okay, we're going to start using your calculator. So, biggest thing to remember is draw a little picture The mean's always in the center of your picture, okay? And let's start practicing with our calculators. So, if I can bring up my calculator here, great. So, here's my calculator. You can see that I've got x is normally distributed. So remember, x is normally with the mean and then the variance. Okay, so standard deviation squared. Always write standard deviation and then squared, okay? So for part A, I want to see x is less than 33. So what you always want to do is draw a quick diagram of that. It's like super quick. So remember, the mean's always in the center, but the mean here is 30. So where is 33? 33 is here. So I'm looking for all the area, because remember, probability is the area beneath that curve, less than 33. And I know, because remember it's symmetrical, I know, just for problem solving purposes, that this half is literally half the probability, isn't it? Each half is 0.5, so I'm expecting my answer to be above 0.5, okay? So what I do is I go to my calculator, okay, so I go menu, and I go 7, distribution, and I'm going to go normal CD, okay? And lower, we're going to put minus 1,000. So remember I said that the x-axis spreads to minus infinity, so the calculator needs something to hold on to. So minus 1,000 is a really good number. So what it's doing is it's doing like this bit, so it's doing it from minus 1,000, but remember our values, you know, the minus 1,000 is so small, the y values, that is basically negligible. So you're going to capture everything between minus 1,000 and beyond, all right? So our upper is the value that we're looking for, which is 33. Okay, so 33. Our standard deviation, as we said, is 4, because remember it's 4 squared is the variance, so 4 is your standard deviation, and your mean is 30. So done, and then press equals, and there we go, there's our probability. So 0.773 if we do it to 3 sig fig. And that makes sense, that much of the curve has been covered, that much area. It's above 0.5, and you can see there's a gap on the right. Let's carry on. So B, probability of x greater than or equal to 24. But what's the probability of x equaling 24? Nothing. So this is exactly the same as the probability of x is greater than 24. Do you see? The probability of x equaling anything is nothing when it comes to a continuous distribution, because it's literally a line, and a line has 0 width, and area dictates probability beneath a probability density function. Okay, so at the moment, if we again we always draw a little sketch, so the mean's in the middle. We're looking for 24, which is here, and everything above 24. So we can see it's all to the right. But our calculators only work from left to right. Okay, so what we're going to do, we're going to have to do 1 minus the probability of x less than 24. So this is less than 24. So if we do 1 subtract all the red bit, then we must be getting our answer. So we're going to go back to that, right? So we got our 1,000, but we want our upper not to be 33 anymore. We want it to be 24. So we can just go for it. So that's where we can do our store A business. And then when we go back, in the upper, we'll go 1 minus, and then alpha A. And then we've got it. So it's 0.933 to 3 sig fig, which again makes sense because I can see it's way above 0.5. And that's a good answer. Okay, so we're boxing our final answers. And we've got 2 more examples. So again, I bring up my calculator here. So this time, remember we've still got x is normally distributed 34 squared, okay? And now we're here. So probability of 33.5x 38.2. So again, we draw a picture. Here's our mean, 30. We've got 33.5, which is here. And we've got 38.2, which is here. So it's all to the right of the mean, okay? So what we're going to have to do, well, I can clearly see I need to go all the way up to 38.2. Okay, so that takes us up to here. and then subtract everything up to 33.5, and that will give us the remaining area, okay? X less than 33.5. So again, I'll use my calculator and use that store button. So my upper is the thing I'm looking for, so 38.2. Okay, so 0.9, so I'm just going to go store A, right, wicked. And then we'll do the same for our 33.5. And then we go store B. And then we go back to our upper, and we go alpha A, subtract alpha B. And then we get 0.1706. So 0.171 to 3SF. Do you see? Cool. And again, that makes sense. It can't be bigger than 0.5, can it? Because it's definitely on 1/2. So that makes sense, and that's why we're drawing that picture. Okay? Part D then, probability of x less than 27 or x is bigger than 32. If we draw our picture, here's our 30 again, remember? So we've got 27 less than, and then we've got 32, which is more than. So can you see we're going to have to add them up? So we're going to have to do probability of x is less than 27, that's that bit. And then we're going to have to add the probability of x being bigger than 32. So what's the probability of x less than 27, that's all good. But the x bigger than 32, our calculators only work left to right. So we want all the area up until that point, 1 minusing it. Okay, so 1 minus the probability of x less than 32. Okay? So again, we could do that. So 27. So we get, so you can just write it out like that if you want to show you're working. Well, I think it's a good idea to do that, to show you're working. And then 1 minus, we can do the same thing. So 32, which is that. And then we could do store A again. And we can go back. We can go 1 minus alpha A. And we get, so I've already done the 1 minus 0.3085. Okay? Add those together. So 0.3085 plus 0.2266. And we get 0.351. 0.5351. So I am doing it in the stats function already to kind of save time, but you've got to be careful with your rounding. So really I should always give it to 3 sig fig because this calculator always does it to 3 sig fig. Okay, how are we doing for time? Okay, nearly there. So just do this 4 more example together then, and then that's the end of this video. So it says an IQ test is applied to a population of adults. The scores X on the test are found to be normally distributed with N being 100. Right, okay, so remember for normal distribution, the bigger the N, the better it is, okay? Because as you can see, it's just a glorified histogram in a lot of ways. So we know mean is 100 and standard deviation is 15, okay, with variance 15 squared. Adults scoring more than 140 on the test are classified as genius. So find the probability that an adult at random achieves genius classification. Okay, so the probability of X is bigger than 140 means you're a genius, and that's what we're trying to find. So we draw a quick graph. We know that the mean is 100, and that's always in the center. 140 is above that. So we're looking for this area here. So just like before, we need to do 1 minus that. So again, I can go to my thing. I go 140, but my standard deviation is now 15, and my mean is 100. So there we go, we've got that. So 1 minus 0.996169, etc. to show my working. But I'm just going to go store A again, go back, 1 minus alpha A, and then we got 0.0038, okay? But it says to 3 sig fig, so that's why it's a little bit dodge using this calculator, like in that way, trying to cut corners. So I'll just do it 0.003831, okay? So it's going to be 0.00 383. So watch out for that question there, because it does say 3 sig fig. And then part B is an extension to that, okay? It says 20 adults take the test, find the probability that 2 or more are classified as genius. Wow, now we've got 20 adults, we've got a finite number of trials. So y is distributed, that's right, binomially with 20, and the probability of success is that you're classified as genius, so 0.00383. So if we want to find the probability that 2 or more, so that's greater than or equal to 2, are classified as genius, that's the same as probability of less than or equal to 1, 1 minus probability of y less than or equal to 1. So again, we go to our distribution, but this time we're going for binomial CD. We've got our variable, x is 1, that's the thing we're looking for, n is 20, p is 0.00383, and then bang, here we go. So 0.99733799266 is our answer there. Okay, so we can cut that off at 3 decimal places or 3 sig fig if we want to. And that's the end of the basics of normal distribution.